Good afternoon to everyone. I welcome all of you to the 89th lecture in the lecture series in nonlinear dynamics conducted by the Department of Nonlinear Dynamics, Bharathidasan University, with the support from PRUSA 2.0. It is my pleasure to introduce today's speaker, Dr. V.K. Chandrasekar. Dr. V.K. Chandrasekar obtained his PhD in physics from Bharathidasan University in the year 2009. He started his academic research career in 2007 as a visiting research fellow for a year in the Lancaster University, UK. He then served as a research associate and then scientist, and also as a senior scientist in the Department of Nonlinear Dynamics, Bharathidasan University. He started his teaching career as assistant professor in Shastra University in the year 2014. He is currently serving as an associate professor in the same university. Dr. V.K. Chandrasekar received Indian National Science Academy's Young Scientist Medal in the year 2010. He was also selected as an associate in the Indian Academy of Sciences during the 2011 and 14. He also received Beauty Foundation Award for Excellence in Theoretical Physics, Astrophysics and Biophysics from Indian Physics Association in the year 2012. And G.T. Naidu Young Scientist Award from Makkal Sindhanai Peravai, Erode, Tamil Nadu in the year 2017. He was selected as a research proposal reviewer for National Science Center of Poland in the year 2018 and in the year 2022. And also served as coordinator for physics, the DST Physics program level 1 in the year 2020. At Shastra University. With this short introduction, now I invite Dr. V.K. Chandrasekar to deliver his lecture. Over to you, Chandrasekar.
Yeah, thank you, ma'am. Good afternoon. Okay, is it visible?
Yes, yes.
Yeah, thank you. Okay, so the title of the today's presentation is the Kuramoto model in the presence of additional asymmetric interaction. My plan of the talk is as follows. First, I briefly introduce about the phase model. Then I derive the Kuramoto model from the phase model, and I show some of the Kuramoto results on it. Then I introduce the asymmetric interaction into the Kuramoto model, and I discuss some of our findings on it. Finally, I conclude my presentation. Complex systems are very common in nature. They are around us in the form of social network, internet, ecological network, and within us in the various form of biological networks and so on. So the studying about the complex networks is a hot topic of research in recent times due to its wide applicability. To understand the complex pattern and collective behavior in complex systems, we have to model the complex systems using the mathematical equations. So networks of coupled nonlinear oscillators serves as a best candidate for this. So in this direction, today I am going to consider one of the mathematical model helps to understand the complex systems called a phase model. So while hearing the word phase, so we have the lot of questions in our mind, like what is phase? What is phase model? How can we derive them? And so on. So in this talk, I'm going to answer some of these questions. Okay, so what is phase? For that, let us consider a particle moving in a one-dimensional Cartesian coordinate direction with a constant velocity v. Then the position of the particle is defined using So defined using this equation, x of t equal to Vt plus x of 0. Here x of t gives the position of the particle in time. We called this as a displacement of the particle from the equilibrium, from the origin. And x of 0 is the initial position or position of the particles. We call this as an initial displacement and so on. V is the velocity of the particle and so on. Suppose if we consider a particle execute the rhythmic oscillation, then if the particle execute the rhythmic oscillation, we want to model this dynamics. The phase and amplitudes are gives the elegant way to represent these dynamics. Using them, we can model the rhythmic particle by defining the dynamics on circle. Let us consider a particle moving or rotating in a circle with a constant angular velocity omega. Then the position of the particle is defined with this expression phi of t equal to omega t plus phi of 0. Here phi of t gives the position of the particle on the circle. We call that as a phase. And phi of 0 is the initial position on the particle on the circle. We call this as an initial phase. And the radius of the circle always gives the amplitude of the rhythmic oscillation. So phase is the angular position of the rotating particle or rhythmic oscillation. Done. What is phase model? Many physical, chemical, and biological systems can produce collective rhythmic oscillation, which elegantly described, mathematically described using the coupled nonlinear dynamical systems. These coupled oscillators interact via mutual adjustment of their amplitudes and phase. When coupling is weak, amplitudes are relatively constant and same for the coupled nonlinear dynamical system. So in this situation, the interaction between the systems only represented by the phase. So now the coupled nonlinear dynamical systems called as a phase model or phase oscillators. Okay, how can we derive this? In order to answer this question, so let us consider a spring mass system with a spring constant K and mass M. So if you introduce a small perturbation on the systems execute a harmonic oscillation about the equilibrium position. In order to find the dynamical equation for the systems, the best way is to identify the force acting on the system. So according to the Hooke's law, the force acting on the system is given by F equal to minus Kx. Once we know the force acting on the system, then we apply this force into the Newton's second law, F equal to ma, and identify the dynamical equation represent this system. So after substituting this force, we identify the equation of motion for the system is mx double dot equal to minus kx. So the acceleration always represented by the double derivative of displacement. Okay, so mx dot equal to minus kx, and rewriting this, we get a standard equation x double dot plus omega squared x equal to 0. We call this equation as a simple harmonic oscillator and so on, due to the nature of oscillation. So here omega naught is the natural frequency, which is given by square root of k by m. So if you solve this second order linear equation, we get the general solution of this form with a two arbitrary constant or integration constant a and phi. We call them as cell amplitude and phase. Since a and phi are constant, so the equation of motion for the a and phi is a dot equal to 0 and phi dot equal to 0. So the plot shows the time behavior of x and phase portrait of the harmonic oscillator. So here it's clearly shows the harmonic behavior of the system. Okay. Okay. So next, I slightly perturb the parameter in the systems. I slightly perturb a spring constant. I slightly vary the spring constant to the system. So if slightly vary the spring constant of the system, so it's automatically change the frequency of the system. So the modification in the frequency from omega naught to omega naught plus delta omega. Here delta omega is very, very small. So I introduce a very slight perturbation or slight modification. I call this modified frequency as omega 1. So now, in the modified frequency, the equation of motion for the system is given by x double dot plus omega 1 squared x equal to 0. Here omega 1 is the natural frequency of the modified system. So the solution of the equation is written as x equal to a1 sine omega 1 t plus phi 1. Here a1 and phi 1s are integration constant for that system. Also, I can write the same solution as a1 cos omega naught t plus delta omega t plus phi 1. Okay. Interestingly, this perturbed solution can also be written in terms of the unperturbed solution, what we have derived previously. Okay, with the change of variables, simply change a as a1 and phi. I define phi as a delta omega t plus phi 1. And the equation of motion for the a and phi becomes a dot equal to 0 and phi dot equal to del omega. So previously a dot equal to 0 and phi dot equal to 0. But here a dot equal to 0, phi dot equal to del omega. If I define a complex quantity z equal to a e power I phi, then the equation of motion in z is z dot equal to I del omega z. Interestingly, we see that the small deviation in the frequency simply modified the phase of the system. So only modify the phase of the system. Okay, so let us consider another case. Here I introduce the weak damping into a system. So here alpha is the damping coefficient, which is very, very less than 1. So this equation is called damped harmonic oscillator. So the system admits 3 types of solution depending on the value of omega and alpha. If omega squared greater than alpha squared, then it admits the underdamped solution. If omega squared equal to alpha squared, it's a critical damped solution. If omega squared less than alpha squared, we have a overdamped solution and so on. But here I assume that alpha is very, very small, so it always comes under the underdamped case. So omega naught squared minus alpha squared always greater than 0 and so on. So this equation admit the solution x of t equal to a2 e power minus alpha t cos square root of omega naught squared minus alpha squared t plus phi 2 and so on. Here a2 and phi 2s are integration constant. And here we know that alpha is very, very less than 1. So I can consider the square root of omega naught squared minus alpha squared is approximately equal to omega naught and so on. Similarly, I can convert our perturbed solution into a non-perturbed form, solution of the non-perturbed equation with the change of these quantities. So a equal to a2 e power minus alpha t and phi equal to phi 2. So now the equation for a is a dot equal to minus alpha a and phi dot equal to 0. In the complex quantity, it's defined as x dot equal to minus alpha z. And this figure shows the time behavior of x and a and so on. Okay. From these two cases, we come to know that a small perturbation in the parameter of the original system approximately modified the amplitude and phase in the original system. Now, the question is it possible to derive this modified amplitude and phase equation directly from the equation, unperturbed or perturbed equation? Yes, we can derive them from the perturbed equation systematically by introducing the multi-time scales, a fast time scale and slow time scale. Here T naught represents the actual or fast time scale, and T of k equal to epsilon kt represent the slow time scale. Here epsilon is the very small parameter. The reason behind the introduction of this different time scale is that the dynamics of the original variable x is much faster than the dynamics of the modified amplitude and phase. For example, consider the damped harmonic oscillator. Here, when x complete a cycle, a varies by a small value. You see that way. A varies by a very small value. So it's clearly indicated that the time scale of x is much faster than the time scale of a. So based on this observation, we define a new time scales or a fast time scale and a slow time scale. So introduction of this multi-time scale, the total derivative d by dt and d squared by dt squared as modified into this form, and substituting this into our perturbed equation, we get this equation with different time scales, d of 0, t1 and so on. So here d2 and so on are observed in this higher order epsilon. To derive this equation, I have introduced this transformation. So I have changed the small parameters delta omega and alpha in terms of epsilon by introducing the new parameters delta omega naught and A. Delta omega naught and A no longer a small parameter. So only epsilon del omega naught and epsilon A is the small parameter. For time being, I omit this higher order term and write this equation and collect the powers of epsilon equal to 0. I get these two equations. The first equation in derivative in fast variable, the second equation is the combination of fast and slow scale. So solving this first equation, I get this solution. So x is a function of fast time scale, but this complex quantity z is a function of small time scale. Okay. So now substitute this solution into the second equation and equate the powers of, or collect the powers of e power I omega t. I get the equation for the small time scale. And simplifying this equation, I get the equation for Ez, dz by dt1 equal to minus a plus I delta omega naught into Ez. Now defining the equation z equal to a e power I phi, I get the equation for a and phi. And introducing the transformation again, I get the equation for a and phi in the fast time scale. Here a and phi in a small time scale with the parameter a and del omega naught. And here I have the equation for the fast time scale in the very small part of the equation. So alpha and delta is small parameters. Here a and del omega naught, it's not on a small parameter, but t1 is the small parameter. Okay. So you see that I get the same equation what we have derived previously by using the solution. Okay, so I can get the same equation from the equation itself. Okay, so this analysis is called multiple scale analysis. Interestingly, the same is applicable to the nonlinear equation also. But the main thing is it should be weakly perturbed nonlinear oscillator. So the nonlinear term should be weak. So the weakly perturbed nonlinear oscillator in general represented by this equation. For an illustration, I consider a van der Pol oscillator, a well-known van der Pol oscillator, well-known limit cycle oscillator. So the equation of motion for the van der Pol oscillator is given by this equation with the parameters omega and a, b, and so on. Here, this omega, epsilon omega, and epsilon a are small parameters, not b. And now I apply the same multiple scale analysis.
There is an x missing in the right hand side.
Yeah, yes. So here it's a x. Yeah, thank you, sir.
Chandrasekar, there is a question in the chat box.
Yes. Yeah. Yes, but here multi-scale analysis for the ordinary differential equation, but the self-Miller analysis are also look similar, but it's for a partial differential equation. A similar analysis we can apply to the perturbed quantic nonlinear analysis equation. Yeah.
Yeah, you can proceed, Sameer.
Yeah, thank you. Okay, so if I apply the multi-scale analysis to this nonlinear equation, I get this equation and omit the higher order terms and equate the powers of epsilon. I get this two equation and solve the first equation and substitute the solution of first equation into the second equation and collect the powers of e power I omega naught t. I get this equation. Yeah, so I get this equation. But here we have two terms. One is slow scale term and another one is the fast scale term. Okay. So to separate this or to remove the fast scale term, integrate this equation with a period 0 to 2 pi by omega naught in the period of fast time scale. So if we integrate this equation, the fast time scale terms goes to 0. So now we have only this slow time scale term. This is given by this equation. Now introduce the change of variables z as z divided by root of ab into this equation. We get the standard Stewart-Landau oscillator equation, the standard well familiar limit cycle oscillator equation. So if you apply the slow time scale analysis to the van der Pol oscillator, we identify the Stewart-Landau oscillator. Now define z as a e power I5. I can separate or I can find the equation for a and phi is given by this equation, and this equation can be solvable. If we solve this equation, it gives the asymptotic solution for this equation. A, capital A equal to square root of small a, phi equal to omega t plus phi naught. And substituting this a and phi into this z equation, we get the solution in terms of z. And write the solution in Cartesian form, we get this solution x of t equal to square root of a cos omega t plus phi naught and y of t equal to square root of a sin omega t plus phi naught. This solution is called a limit cycle solution because whatever be the initial condition on the systems, in the asymptotic limit, the system settle into an isolated periodic orbit. If initial condition inside the closed orbit or outside the closed orbit, asymptotically, the system settle into an isolated closed orbit. Here, the radius of the closed orbit is root a. So this type of isolated closed orbits are called limit cycle. The system exhibit this type of isolated periodic orbits are called limit cycle oscillator. Okay, so next I consider a coupled nonlinear oscillator. Since a coupled nonlinear oscillator is the best candidate to study the complex systems. Okay, so for that I consider weakly coupled nonlinear oscillator of this form. Okay, so here epsilon gk represents the weak interaction between the oscillators. So again, for an illustration, I consider van der Pol oscillator or coupled van der Pol oscillator with this type of coupling. Here, KJL is the coupling parameter. In general, it is defined as K into AJL divided by QJ. Here, capital K is the coupling strength between the oscillator. AJL is an element of adjacency matrix A, giving detail about the coupling links between the oscillator. AJL equal to 1 if J and Lth oscillator are coupled, otherwise it's 0. And Qj is the degree of Jth oscillator. Now applying the multi-timescale analysis to this coupled van der Pol oscillator and equating the powers of epsilon and solve the first equation and substitute in second and so on and averaging, finally we get this coupled Stewart-Landau oscillator. If introducing the transformation is that say equal to aj e power theta j, we have the equation in terms of aj and theta j. In the weak coupling limit, we can neglect the deviation in amplitude due to the coupling. So we have aj equal to a. So in this case, if aj equal to a, then al by aj goes to 1. In this situation, the phase equation decoupled from our amplitude equation, and which is given by this form. So now we have only phase equation in the weak coupling limit. When we consider the globally coupled case, that is QJL equal to K by N. All the oscillator in the network coupled to all the oscillators. We call that as a globally coupled oscillators. In that situation, this phase equation becomes a Kuramoto phase equation. Okay. So Kuramoto in 1979 solved this equation analytically and found the analytical solution for the synchronized state and so on. So we call this phase model, phase equation as the Kuramoto model. This type of globally coupled systems observed in nature, like collective emission of light pulse for flies, synchronized pulse by cat, coordinated firing by cardiac pacemaker cells, rhythmical clapping in a large auditorium, and synchronization of neuron in the central nerve systems, and so on. So to analyzing this type of globally coupled oscillator help us to understand many natural phenomena. So in 1979, Kuramoto solved this globally coupled phase model and found the analytical expression for the synchronized solution. In this equation, theta I is the phase of the jth oscillator and omega j is the natural frequency of the oscillator. and K is the coupling strength. In the past 40 years, this Kuramoto model has extensively studied in various aspects, since it served as a best model to study the collective synchronization. To solve the equation, Kuramoto introduced the order parameters.
Yes. I have a small doubt in the previous slide. Is there any way to calculate the number of limit cycles in that system mathematically? Suppose if I take 3 oscillators or 5 oscillators, then is it possible to calculate the number of limit cycles?
Yes, no. If you identify the apply the multi-time scale analysis. Hello.
Yes, I am here.
Yeah. Then you get an amplitude equation for that original nonlinear equations. If you analyze the original nonlinear equation, if you analyze that amplitude equation, we can able to say the number of limit cycle exhibited by this system.
Okay, thanks.
Yeah. Okay, so Kuramoto introduced 2 order parameters, R and psi, to solve the model. This R and psi is related to the phase of the oscillator through this relationship. Here R is called phase coherence and psi is called as an average phase of the model. Here R varies from 0 to 1. Based on the value, it gives the synchronization inside the system. If R is 0, represents desynchronized or incoherent nature of the system. Since in this state, all the oscillators oscillate or rotate with nearly their natural frequency with random phases. In the non-analytical oscillators. So due to that, we have R equal to 0. In the complete synchronized state, all the oscillators oscillate or rotate with a single frequency and phase. Due to that, R takes the value 1. But in the partial synchronized state, partial oscillators oscillate with the same frequency and phase, and the remaining oscillators draft with the different frequencies and phase. Due to that, R takes the value between 0 to 1. So the order parameter R is used to measure synchronization. Sometimes it's called as a measure of I forgot the name. Yeah. Okay. So the order parameter is used to measure the synchronization.
There is one more question in the chat.
Yes.
So you want to answer now?
Chat box.
Yes.
Yeah. Yeah, mostly in the identical systems, it may be refers as the anti-synchronization and so on. But if you go for the non-identical systems, it refers as the synchronization.
Okay, Prasant, is that clear? Yeah.
Okay, thank you. Okay, now substitute this order parameter equation into the original equation. Kuramoto convert the coupled phase model into a mean field model. Here, the oscillators no longer coupled, they only coupled to their mean field. Okay, so this is an interesting transformation. And so once he transformed the original equation into a mean field equation, then he used Lorentzian frequency distribution into the model and identified the threshold coupling above which the system shows the synchronization behavior. The threshold coupling is Kc equal to 2 by pi g of 0. He also find the asymptotic value of the synchronized measure, that is order parameter R, for the non-zero R value. So R equal to square root of 1 minus Kc by K. So the figure shows the behavior of R for K less than Kc. When the coupling is less than the critical coupling, the order parameter asymptotically goes to 0. When K greater than Kc, the order parameter takes some non-zero positive constant. If K tends to infinity, then R goes to 1 and so on. So this figure shows the behavior of R as a function of the coupling constant. When the coupling K is less than some critical coupling, less than this critical coupling, so R takes the value 0. So here all the oscillators oscillate with our random frequencies and phase. So when K greater than Kc, oscillator with a very nearby frequencies locked themselves and oscillate with the same frequency, form a synchronized, small synchronized clusters. And the remaining oscillators oscillate with the random frequencies, and we call that oscillator as a desynchronized oscillator. So when K greater than Kc, we have a small synchronized cluster and desynchronized cluster. Due to that, R takes small positive values. Now, increasing the K value slowly, the number of oscillator in the synchronized cluster slowly increase and number of desynchronized oscillator decrease. So due to that, a slow variation of R happens. So when K reaches the large value, all the desynchronized oscillator tends to synchronize and form a single synchronized cluster. So R takes the value 1. This type of phase transition from desynchronized state to a synchronized state, called a continuous phase transition. This type of continuous phase transitions are called as a second order phase transitions. However, the phenomena of explosive synchronization, where asynchronized oscillator abruptly undergoes synchronization in the complex systems, is often observed in brain activities during the anesthesia induced unconsciousness, Parkinson's disease, and so on. This type of discontinuous phase transition called as a first order phase transition. This type of first order phase transitions also observed in the Kuramoto model with an non-trivial extension. This explosive synchronization observed in the Kuramoto model in the following settings: network with positive correlation between the natural frequency of the oscillator and the degree. Model with adaptive coupling. So coupling also varies with respect to time. Kuramoto model with additional higher order interactions. Multi-layer and multiplex networks and so on. These are non-trivial generalization of the Kuramoto model, but no observation in globally coupled model. Simple Kuramoto model with trivial extension. We have identified that explosive synchronization happen even in the globally coupled Kuramoto model when we introduce an additional asymmetric interaction. So this asymmetric interaction. If epsilon 2 is 0, this equation is the Kuramoto model. This equation is invariant under the transformation theta j equal to omega t plus theta j. This type of invariant property is called as a rotational symmetry of the system. So when we introduce this additional interaction, the systems no longer invariant under the transformation theta j equal to omega t plus theta j. So this terms breaks the rotational symmetry of the system. So that's why this term is called as, or interaction called as, a asymmetric interaction. So here epsilon 1 and epsilon 2 are coupling constants, symmetric and asymmetric coupling constant, and omega j is the natural frequency of the oscillator. So we have also introduced the order parameter for the systems and convert the system, coupled system, into a mean field coupled system, and analyze the same system for the Lorentzian distribution of the frequencies. Here gamma is the half width and half maximum of the distribution. Omega naught is the natural central frequency of the distribution. To get a global picture of the dynamics, we have introduced the time average order parameter, capital R. While analyzing this system by varying the epsilon 1 and epsilon 2, we have identified the three states: incoherent state or desynchronized state, standing wave state, and stationary synchronized state. In the incoherent state, all the oscillators are oscillating with random frequencies. So to do that, R under time average R goes to 0, take the value 0. But in the standing wave state and the stationary synchronized state, we have a synchronized cluster as well as the desynchronized cluster. The number of synchronized cluster oscillator in the synchronized clusters depends on the coupling strength of the system. But in this standing wave state, the synchronized clusters, also the desynchronized clusters, desynchronized oscillator, oscillate with their angular frequencies. Due to that, we have an oscillating nature on the order parameter. Due to that, we have a non-zero average R, since we have a synchronized cluster. But in the stationary synchronized state, we have a synchronized cluster and desynchronized oscillator, desynchronized phase with zero frequencies. So due to that, R takes the constant value, R dot equal to 0. Okay. So this state emerged due to the introduction of the asymmetry parameter. Here the incoherent state, standing wave states are similar to the Kuramoto model, but the stationary synchronized state induced due to the introduction of the asymmetric parameter of the system. To get a clear picture about the transition, dynamical transition of the systems, we have plotted two-parameter bifurcation diagram in the epsilon 1, epsilon 2 plane for gamma equal to 0.5 and omega naught equal to 1. So when the asymmetric coupling term epsilon 2 is less than to some critical value, we have a standard Kuramoto type transition. So incoherent to standing wave, a second order phase transition. When we increase the coupling strength epsilon 2 and the coupling strength nearly greater than the critical coupling, and increasing the coupling epsilon 2, we observe two second order phase transitions. So one is from incoherent to standing wave, another one from standing wave to standing wave state to stationary synchronized state. So we have two second order transitions. And further increasing the value of epsilon 2, we have observed the interesting result. We have one first order and one second order transition. We have a transition from incoherent state to standing wave state through a second order transition, but the transition from standing wave to synchronized state happen through a first order. Due to the emergence of the first order transitions, we have a bistability between the state standing wave and synchronized steady state, which is given as the region R2. And further increasing the coupling, we have a first order transition from incoherent state to stationary synchronized state. Due to that, we have a bistability region R1. Also, the higher value of epsilon 2 completely suppress the standing wave state. So the introduction of the asymmetric interaction, we have a new state. Also, we have a multistability region. Due to the multistability region, we have a first order transition. So to compare our phase diagram with the Kuramoto phase diagram, I have plotted two phase diagram here. So in the epsilon and omega naught space, so in the Kuramoto phase transition, only we have a two state, incoherent to standing wave. But here we have a three state, incoherent, standing wave, and stationary synchronized state. And also we have a multi-stability region. Due to that multi-stability region, bistability region. So due to that bistability region, we have a first order phase transition, as well as in some regions, second order phase transitions. We have also find the analytical stability condition for all the state in the thermodynamic limit using the Art and ansatz. So using the Art and ansatz, we have reduced the low dimensional equation for the original model, and from this low dimensional equation, we have find the analytical stability curves for the collective all the three states, and we found that our analytical curves exactly match with our numerical findings.
Someone said, what is epsilon 1 and epsilon? Yeah.
Sorry, epsilon
1. What is that?
Epsilon 1 is the coupling strength of the symmetric term. Epsilon 2 is the coupling strength for the asymmetric term.
Okay. So you got a condition, right?
Yes. Condition between these. We have also verified the generality of the result for the Gaussian frequency distribution. We have identified the new state and multi-stability and first order phase transition and so on in the system. Then we have introduced the same asymmetric interaction in the Kuramoto model. Here alpha is the asymmetry parameter. If alpha and epsilon 2 is 0, then this equation is the Kuramoto equation. If epsilon 2 is 0, then this equation is the Kuramoto model. When we introduce this asymmetric parameter into this equation, interestingly, due to the asymmetric parameter, we have identified tri-stability region. So previously we have only bistability region. So stability between the incoherent stationary synchronized state and stationary synchronized state to standing wave state. But here we observe the dry stability between incoherent standing wave and stationary synchronized state. Here the stationary synchronized state refers as the OD and the standing wave state refers as the OS. Also, we have identified the bistability between the incoherent state to standing wave state. Okay, so previously the transition from incoherent to standing wave always happened through a second order transition. But here we have identified that up to some critical value of epsilon 2, it happened through a second order transition. After that, it takes the second order transition. Okay. So introduction of asymmetric parameter, we have a dry stability, also one more extra bistability region in the Kuramoto model. Interestingly, also we have found that our model is the variant of Wien-Free model. Wien-Free model is a pulse coupled oscillator model. In Wien-Free, introduced this model to investigate the synchronization of the large population of biological oscillators. In 1967, the proposed theoretical model is given by this equation with the two terms Q of theta and P of theta. Here Q of theta called as a sensitive function, which determines the response of individual oscillator to the mean field. So P of Q theta. and P of theta called as a phase dependent influence function. This always a pulse shaped function. That's why this model is called pulse coupled oscillator. The phase dependent influence function is also called as a phase response curve. While rewriting our equation, we have identified this form. See that it looks similar to a Wien-free model, but with two sensitive functions and phase influence function. When epsilon 2 equal to 0, our model goes to, and alpha equal to 0, our model goes to Kuramoto model. If epsilon 2 equal to 0, our model goes to Sakaguchi-Kuramoto model. But if epsilon equal to epsilon 2, you see that F2 goes to 0, which looks similar to a Kuramoto model. But if epsilon 2 not equal to epsilon 1, we have a two sensitive function, phase dependent function. So that's why we call this as a variant of Kuramoto model. So a variant of Wien-free. Okay, so our model act as the bridge between Wien-free to Kuramoto. Okay. So we have analyzed the influence of asymmetric interaction in the Kuramoto and Sakaguchi-Kuramoto model and find the first order phase transition between various collective states and found many multi-stability and bistability and tri-stability regions. We have identified that our model shows the rich bifurcation diagrams compared to the Kuramoto model, and we have deduced the analytical stability curves for all the states using the low dimensional reduction. And we have also found that our proposed model acts as a bridge between Kuramoto and Wien-free model. Thank you.
Thank you, Chandrasekar. So this forum is open for questions, doubts, clarifications. Yeah, Prashant, you can raise your question now.
Hello, sir.
Yes.
Sir, you told that the coupling strength varies with respect to time. So, at a time, in one slide,
Coupling strength
can vary with respect to time for a system.
not varies with respect to time.
It does not
also it's a function of dependent variable. Varies with respect to relationship between the phase. That type of equation. Okay, so maybe I will go to that slide. So, yeah, here we call that as a adaptive coupled systems. Yes.
Okay, so it is a variation with respect to phase, not with respect to time.
Yeah, if done. If vary with respect to time, we call that as a time varying coupling, not an adaptive coupling. So adaptive means it depends on the system variable as it. Adapt to the behavior. The coupling should be adapt to the behavior of the system.
Behavior means that it should be mainly a function of phase, not time. Like
yes.
Maybe
yes,
indirectly.
Yes.
Okay.
Yes.
Thank you, sir. Sir, and about the tri-stability region, I
Yes.
could not get the point, like how one particular phase can have a probability to go to another phase at the same time. So tri-stability region.
Yeah, maybe bistability and tri-stability are similar. So we have a initial condition, for the system. So if you, depending on the distribution of the initial condition, the systems may go to any one of the state.
Actually, sir, is it possible to write a Lagrangian for such kind of system? Like, for example, if I have a system which goes from one state to another state, A to B, I can find out a Lagrangian. But if I have a system which can go from A to B or A to C, is it possible to write a Lagrangian for such kind of system? Because I do have two kind of final destination from the point A. So.
No. The Lagrangian the definition is given for we have actual path and we have a deviated path. We consider that deviated path is the but here it's happened on real. It depends on the initial condition. Okay. That Lagrangian path, it's for a given initial condition. We have assumed the different path and so on. But here it's entirely different from that.
Okay, sir. So it also depends that how many states are there. There are like that number of stability. Like if there are n possible states in the system, I can say there can be n stability region. So bistability, tristability, and above that also I can assume if I have any states.
Yeah, we have large number of stability. But if you only consider the collective states.
Yes, sir.
I'm not interested in the microscopic behavior of the systems. I'm only interested for the macroscopic behavior of the system. In that situation, the system submits only tractable and basic.
So here in this particular diagram, the R3 region is look. So I didn't get that which point is that from where I could have a tri-stability condition in this diagram. Can I?
Yeah. So in this region, so you see that. Okay,
sir. Okay.
So the region bounded by this dotted line and blue line, that solid line.
Okay, sir.
We have a tri-stability. It's very small region.
Okay, sir. The physical examples would be there, right? So like because mathematically I can see here, is there any physical example also that I can assume of tri-stability?
Yeah, you can go for any non-actually model. This is the
yes, sir.
This phase diagram is valid for mostly all weakly coupled nonlinear systems. Okay?
Oh,
so that's the main point. Here. So you have this type of weakly coupled nonlinear systems, and they expand this expansion of these systems. You maybe get this type of van der Pol type model. Okay, so appropriate value of coupling, you can get this type of tri-stability.
Okay, sir. But for the strongly coupled, it might be not possible.
Yeah. Strongly coupled, you have to concentrate on amplitude as well.
Amplitude as well. Okay.
So you have to solve this whole system.
Yes.
A and theta.
Okay. So thank you, sir. Thank you so much, sir.
Professor Ambiga, you can raise your question now.
Towards the end, you are showing a case where you have second order as well as first order transitions, where the order parameter was never reaching 1. Then what do you think about the order or synchronization there? It's less than 1.
So here, ma'am?
Yeah. So,
so here I can say that there exists a desynchronized oscillator. So only in the incoherent oscillators R reach 1 only for k tends to infinity. So for finite value of k, it's nearly takes the value 1. So that's why. So still there exists some desynchronized
so then what
oscillator.
is the transition to? Transition is to which state? What type of state?
So here. Yeah, stationary synchronized state.
Stationary synchronized state. Okay.
We call we call that as a stationary synchronized state, means there exists a synchronized cluster in the whole group. So for that, we call that as a synchronized. But still, there is some few desynchronized oscillator exist on.
But can we say there is frequency synchronized?
Yeah, still, but here the phase model, we introduce of the phase, only we have the correlation between the phase. Yeah. So even if frequency synchronized and with random phases, the order parameter shows the null.
Okay.
But this happen only for identical oscillator. If you go for non-identical oscillator, always.
Okay, thank you.
Yeah, thank you.
Excuse me, sir.
Yes.
Sir, actually, I have basic doubt on the synchronization. In the some of the literature, they also say for the asynchrony or anti-synchrony, I didn't remember what they write. It refers to they are synchronized in opposite phase, not in phase. They are synchronized to oscillate in opposite phase. So R equals to 0 was correspond to the synchronization where they are synchronized in opposite phase, or there is a no synchronization, because if it says R equals to 0, physically I can assume that it should be no synchronization. They are just randomly oscillating, but
yeah. So okay. So I catch your point. Yeah. So even if you have a large number of oscillator, all the oscillator uniformly distributed from 0 to pi, you assume that all the oscillators are oscillating with the same frequency. Okay. But the phases are distributed from 0 to 2 pi. Okay. Yeah. So in that situation, yes, R takes the value 0. Okay. So even for that case. But in the same case, even with the oscillator oscillate with same frequency, but the half of the oscillator oscillate in one phase and half of the oscillator oscillate with the antiphase. Okay. So the phase difference between these two are pi. Then we call that antiphase and so on. Okay. In that situation also, the order parameter shows the value R equal to 0. Okay. But if we have a different number of oscillator on both group, then R takes the non-zero values and so on. To validate or to identify to get the more clarity, you have to introduce the higher order parameter. Okay. So you take instead of taking summation of e power I theta j, you have to take e power I2 theta j and so on. So in that situation, even you have an anti-synchronization, the order parameter takes the value 1. Okay. Is it clear?
Yes, sir, it is clear now, sir. And those kind of situation is included, sir, in which I can think of that synchronization not in 0 or pi, but instead I can think of synchronization with the phase difference any phi number.
Yeah, you can introduce you always also verify the higher order parameters, like include the 2 I theta and 3 I theta and 4 I theta, like that. You maybe get the number of cluster states inside the group and so on. It gives the clear picture on the number of clusters, synchronized cluster inside the.
Okay. Clusters means the groups are.
Groups are separated by antiphase and so on.
Okay, sir. So thank you so much, sir.
Yeah.
Chandrasekar, what are the features that are different in Winfrey's model compared to Kuramoto model?
Yeah, in the Winfrey model.
Yeah.
Yeah. So actually, this is the phase diagram for the Winfrey and Kuramoto. Actually, this is the so maybe some modifications, but this is the phase diagram for the Kuramoto, and this is the phase diagram for the Winfrey. Since here we assume that epsilon 1 equal to epsilon 2 equal to epsilon, so here I mentioned that if epsilon 1 equal to epsilon 2, we have a only one phase dependent phase influence and sensitivity function and influence function. So in that situation, our model is equal to the mean free model. In that case, we have this phase diagram. So this phase diagrams resemble to the mean free phase diagram.
So in the Winfrey model, you say that there are 3 distinct states.
Yes.
Whereas Kuramoto model, there are 2 distinct states.
Only 2. Also, there exists a multi-stability and first order transition and so on.
Okay, thanks.
So, are there more questions? Or clarifications? Yeah, we are not getting any questions. So, I would like to conclude the session by thanking Dr. Chandrasekar for accepting our invitation and giving a very wonderful talk, which is very helpful to many students, I believe. So, thank you very much, Chandrasekar.
Thank you.
Okay. I will write to you the other details by email.
Okay.